In this video, we're going to build towards understanding the definition of a derivative. And we're going to start by comparing what we already know regarding average and instantaneous rates of change. Now, average rate of change is the slope between 2 points, in a sense, the slope of a secant line. So slope, we know how that's defined. We talk about slope and we say change in y over change in x. And we developed this a plus h minus f of a divided by h definition. We developed this, we worked with this in our previous sections. Different from a secant line, we have tangent lines. And tangent lines touch a curve exactly or at only 1 point. So again, if we think about our curve and I think about my secant line between those 2 points, that line sort of mimics that rate of change. But if we think about at this initial point we looked at here, I'll call that P. If we think about drawing a tangent line, that slope is actually a bit different. So a tangent line touches a curve at exactly 1 point. So I've brought in a visual here because we're really going to, compare these ideas of a secant line to a tangent line. So think about this point R, which begins at A, and S, which we could call B, or is actually H units away. That distance between A and B is H units away. So we'll call that A plus H. So we have A, F of A plus H, F of A plus H. And you see that definition building here. So the change in Y, my vertical change, divided by the change in X, A plus H minus A, gives us just that H value. And I'd like to take a minute and talk about what that H is. H is really just the way of writing change in X with one symbol. H is this horizontal distance. If we think about our algebra definition of slope, x of 2 minus x of 1 being in the denominator, or a definition we previously defined in this class, we said b minus a if this was point A and that was point B, or rather just change in x or h. So keep that in mind as we work through this, that h represents the change in x. Now back to our graph. If we think about drawing that secant slope through a point, say S sub 4, which is closer to that initial point R. So we think about shrinking S sub 1 to S sub 2 to S sub 3 to S sub 4, and these 2 points, R and my S point, are becoming closer and closer together. And what you see is as that S sub 1 becomes S sub 2, becomes S sub 3, becomes S sub 4, this secant line here from R to S sub 4 is closer to the tangent line. So the question is how close can these 2 points become together? S sub 4 could be S5, etc. It doesn't really matter what that subscript is, but the idea is we can become infinitely close. So dragging this point infinitely close to where those 2 points are essentially right beside each other, or maybe even on top of each other, right? If they're infinitely close, we're going to get a really good tangent line approximation. But the issue is if they are the same point, if this is so close that it's actually right on top of it and it's the same point, how far apart are R and S? What's that H that we're going to be dividing by? And if they're so close they're touching, there is 0 distance between them. All right, so keeping that in mind, because as we develop our definition of a derivative, we're going to end up using a limit, because we're going to essentially say, hey, this point in the denominator cannot equal 0, but what happens as we approach 0? All right, so that's the idea of what we're dealing with here. So now let me define for you the slope of the tangent line. So here's my definition for slope of a tangent line. And the tangent line of the graph of this function at the point of consideration a comma f of a is the line through this point having the following slope. So this is now my slope formula here. We have our difference quotient, which represents slope, and we're saying, well, let's look at what happens as the distance between those two x values is so close that there's essentially no distance. They're almost the same point, and the limit of that horizontal change is approaching 0. And of course, this definition works provided our limit exists, because if the limit doesn't exist, there will be no tangent point there. So this is where we bring in our new calculus word, derivative. Derivative of the function is defined as this formula, f prime of x equals, and if you look at what we have here, isn't this the definition of the slope? So the limit as h approaches 0 of the quantity f of x plus h minus f of x, all divided by h. So the derivative and the slope of the tangent line are the same thing. Now, talking a bit about the notation, f prime of x is what we have there. F prime of x is how we read that, and that means the derivative. So this prime, this little apostrophe that we put between the f and the parentheses x, that's what indicates derivative. And there are other ways that we can write derivative, but the main way we're going to focus on in this class is f prime of x. As we move more into calculating derivatives, I'll show you different notations, but for right now, we are going to use this prime notation. Okay, so we have identified now that the slope of the tangent line is the derivative. This is my derivative. And if we know the slope of the tangent line, if we know a slope, we can find that derivative. We can write the equation of the tangent line at that point. So this is just our point slope formula that we're looking at here. So thinking about what we have y minus some y sub 1 value equals m, keeping in mind our derivative at the point represents the slope, times x minus x sub 1. So this is just algebra. This is the exact same as our point slope equation that we learned in our algebra class. And this is just the way we can write the equation of the line. So now that we have addressed these definitions, we know what slope and the derivative are. Slope of the tangent line represents the derivative. Let's do an example where we find the equation of a tangent line at a given point. As you can see here, we are given a function f of x. F of x equals x squared plus 2. We're going to determine both the slope of the tangent line, which we've defined is the derivative at that point, as well as the equation of the tangent line. And the point of consideration in this case is 2, or our a value is 2. So let's jump in to calculating this slope. So by the formula, we need f of a plus h. That's going to be f of 2 plus h. That's going to give me this first piece that I'm going to plug into my formula. F of 2 plus h is the quantity 2 plus h squared plus 2, which we can simplify. That is 4 plus 4h plus h squared plus 2. And f of a, that's where I will plug my 2 value in, which gives me 2 squared plus 2. 2 squared is 4, plus 2 gives me 6. So now that we have those two pieces, let's plug them into my slope definition or my derivative. M equals the limit as h approaches 0. 4 plus 4h plus h squared plus 2, the 4 and the 2 give me 6, plus 4h plus h squared, minus f of 2 is 6, all of which needs to be divided by h. If I look at plugging 0 in for h, I can't do that right now. So this is where we have to cancel that. Now we've mentioned this before, 6 minus 6, those should always reduce. Whatever we have here should always nicely, completely cancel out with something in the first half. So here I have the limit as h approaches 0 of 4h plus h squared divided by h. You notice both terms in the numerator have an h in them. So that's h times 4 plus h over h. My h values cancel. Now I'm calculating here the limit as h approaches 0 of 4 plus h. I can plug in 0, so that's 4 plus 0, or 4. 4 represents my slope. This is the slope of the tangent line. So I know my slope is 4. So we know the slope of the tangent line is m equals 4. We need to write the equation of the tangent line. Remember, the equation of a tangent line is just like our point slope formula. We need a point and a slope, which is the derivative. So my point, I only have an x value. Is there an easy way I can go about finding the corresponding y value? Well, that would just be as simple as plugging it in to this function. So f of 2 is 2 squared plus 2, or 6. So that means 2, 6 is a point on my graph. I just took my 2 and I plugged it into the function. So the function gives me my output value, and the derivative essentially is giving me the slope of the tangent line. So if I want to write the equation, that's going to be y minus, my y1 value is 6, equals m. M is 4, that's my derivative, times x minus 2. So at this point, we just have to simplify a little bit here. Y minus 6 equals 4x minus 8. Add the 6 to both sides. Y equals 4x minus 2. So what I have here, this is the equation of the tangent line at that point. So let's go back up to the top, look at our function, look at the graph, and relate, this point and this tangent line and this slope, all of this to the graph that we can pull up on our calculator. So I've cleaned my screen up a bit here. We have our original function. We have the point 2, 6, which is a point on that function. We know the slope of the tangent line is positive 4 is increasing, and we know the equation of the tangent line. So what does the graph of f of x look like? Well, it's a parabola opening up with a y-intercept right here at 0, 2, and the point 2, 6. Now this is not to scale, but 2, 6 is a point on the graph. And if I looked at drawing my tangent line, and I've had to kind of draw it a little off so that it sort of looks right, but if I looked at drawing the tangent line, if you graphed both the function and this tangent line on your graphing calculator, what you're going to see is that tangent line is going right past the graph. It's touching at only one point, this ordered pair 2, 6. It's not crossing through the graph, it just touches. It has a y-intercept of -2 and a slope of +4. So just trying to relate all of that together is really what we want to be thinking about. Of course, you are going to have your graphing calculator on the test. So if you know how to use your calculator to help you, this is going to make your life easier. So let's conclude this video. I know this is kind of a long video, but I had a lot to talk about. So we've discovered what slope of the tangent line is, and we can directly calculate that slope if we are given some specific a value, some point of consideration, some x that we are looking at. Now I want you to notice the derivative doesn't have a point. The derivative is going to find the general derivative. So we could go through this process and we'll practice finding the derivative in future examples, but the derivative has x here, not an a value. So if we found the general derivative, we could then at the end plug in any x value we wanted and determine what the slope would be at that specific point. So I hope you guys understand and connect this idea of slope to the derivative, and you have you just feel better about this. As always, if you have any questions, please feel free to reach out because I am here to help. I'm ready and more than happy and willing to help you guys. So I look forward to hearing from you. Thanks and have a good day.